Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 21, and we are talking about randomized complete block designs, and this is part 2 of 3. And actually, there's going to be 4 total parts when we count the video for the code. All right. So I do want to mention that I had this reverse last time. I was saying complete randomized block design, but it's really a randomized complete block design. Okay, so we have the complete block design, and this is a randomized version of it. So I apologize for the mix-up from the last video. Hopefully it doesn't mess you up too much. So we introduced the models, and we talked about this model and what it does and how we block out a nuisance factor, and we defined a nuisance factor not as something that's unimportant, but as something that we're not interested in studying. In our example, we had a hardness tester, and we wanted to test the 2 tips to see if one of the tips had more variation, or if it's fixed effects, which I believe it was. There's 2 tips only, that one of the tips resulted in a different mean than the other tip. And so that's what we were testing with fixed effects. But if we did a complete randomized design, or we did a complete randomized design, no block in there, then raw material would be different. And so it may add an effect, a additional error to the results, and muddy up the water, or cloud the results, or dilute the results, or hide certain results, or emphasize results that aren't there. It just can give a false picture, okay? Because it's a source of variation and we're not accounting for it. We're not interested in studying the material, maybe, because the material, studying the material is a separate study, really, to see how consistent it is between batches or heats and what have you. And if we're purchasing the material from a supplier, we only have minimal amount of control over that supplier. Usually there's federal specifications that they're making the material to, if it's a alloy, and so, which most things are. So there's this federal specification that says here are the limits, and you can't expect them to do better than that tolerance on the different impurities, etc., unless you pay a lot extra. And even then, some places will say there's no way we could afford to make that for you, and you couldn't afford it if we did, so you're stuck with what you've got. So I hope that gives you a perspective that it's not that material was unimportant in that case. It was just that the scope of controlling it in that experiment is, or that experiment has really very little to do with trying to see the effects of the material. It's more about, we're more interested in, is there a difference between the hardness readings of one tip versus the other? And we blocked it with material, so we took a hardness measurement with tip number 1 on one portion of the metal coupon, and a hardness reading on the other portion of the metal coupon with tip number 2. And so we say, well, on that coupon it should be fairly homogeneous in hardness from one side to the other. It's a small coupon. And so those 2 readings should be, for all practical purposes, the same. And so we've taken that difference of material out of the equation. We've blocked for it. Okay. So now let's talk about if we have a fixed treatment effect, then how do we write the model? So the first thing, of course, is the hypothesis statement. And if it's fixed effects, it makes sense to use this model. It also makes sense to use this model, okay? So, and we've seen, or hypothesis statement, and so, yes, with each, and I'm sorry, I left off in the model, because that is important. Yij equals mu I plus beta j plus epsilon ij. And in this model, it'd be yij equals mu plus tau I plus beta j plus epsilon ij. Okay? So remember to include your models. And so that is the hypothesis that we can use. Now, we talked about all of that last time, and so we want to talk about multiple comparisons this time. So the first multiple comparison that we can do is a Bonferroni method. Okay, and so what we do is if we have m simultaneous confidence intervals, and this is for the treatment means. And remember that these confidence intervals for the treatment means only make sense if we have a fixed treatment effect. Otherwise, it doesn't make sense, okay? And we don't do it. So we don't do confidence intervals or contrast on random effects. We only do it on fixed effects. Okay, so you've seen this equation before. yi dot bar plus or minus t alpha over 2, and both of these are in the denominator. So if there are m simultaneous confidence intervals, if we want the Bonferroni method, then it's really alpha over 2m. And that's a conservative estimate. If we want just the LSD, the least significant difference one, then we would just use alpha over 2. And so that does not control for experiment-wise type 1 error. This Bonferroni method does. So we have the degrees of freedom of MSE. So that's another way of writing this, but it's a little messier. To write df and then ms of e. So I wrote df, degrees of freedom of the error. And then times the square root of MSE over n sub I. Of course, if it's a balanced design, then this is just n. But if it's not, this works for unbalanced designs as well. And so we can calculate those. And again, if we don't want to use Bonferroni's, we want to use Fisher's least significant difference, then just change this m, just leave out this m. And we'll have t sub alpha over 2, and we'll have the confidence interval that way. All right. Pairwise comparisons, we can again use Tukey's, we can use LSD, Bonferroni, Scheffé as well. I did not include that here, but you can use Scheffé's method as well. So again, these are only valid if you have fixed effects for the treatments. And we've seen these equations before, so I'm not going to go over them in detail. You can see that we're using the Tukey critical value here, and then for LSD, and these are differences. These are contrast or pairwise contrast or pairwise comparison. So they're differences in the means, pairwise. And so we can use Tukey's method here, which means there's a 2 here, or we can use LSD, which there's no 2, and Bonferroni, again, there's no 2 here. All right? So those are the comparisons. So really the same as what we've seen in the one-way ANOVA here. And we don't ever do contrast on the blocks. It just doesn't make sense and it's not valid. Okay? We can't, if we had time to go through the regression aspect of ANOVA, we would go through the linear equations and you'd see that there's absolutely no way to solve that system of equations for beta j, if you would. Okay. Now, the additivity of the model. What does this mean? You see plus signs everywhere. That's an additive model. Okay. So this model is completely additive. And it's completely additive because there's no interaction. And we just have k equal to 1, so we can't really test for interaction either. And we're going to talk about that a little more. We'll talk more about this in Chapter 5, which is our factorial designs, when we actually go over how to test for interaction and how we deal with interaction. All right, so since k is only equal to 1, you don't see k in the model, do you? If it was yijk, then we would have mu plus tau I plus beta j plus tau I beta, oh wait, sorry, wrong one. Then we would have tau I, no, not I, tau beta ij plus epsilon ijk. All right. And this would be our interaction term where we're multiplying, I know that's messy, where we're multiplying tau times beta. So tau times beta ij. Okay. So this is an interaction term. And it's not multiplicative. It's a product. So this is not a completely additive model. It's an additive model, but it also has a product in there. Okay. So so our model here is additive because there's no interaction. For example, let's say that we have fixed effects. Remember, both the blocks and the treatments are fixed in this model that we're saying. And so we would have sum of tau I is equal to 0 and sum of beta j was equal to 0 for the fixed effects. So if tau 1 is 5 and beta 1 is 3, then y11 on average increases by 5 plus 3 or 8 for treatment 1 and block 1. This would be above or in addition to the overall mean. Okay, so it would be basically, this means it would be mu plus 8, okay, for the average. Okay, so that's what we mean by these treatment effects. Interaction. Let's talk about some interaction here, and we'll start off with an example. Let's say we're going to compare 4 different formulations of some chemical product. And we're going to select this across 6 batches of raw material. So the batches of raw material are going to be considered blocks. If batch 2 has an impurity that adversely affects the yield, which would be our output here, but does not affect the other formulations, so just one batch, so it doesn't affect the other formulations or other batches, then an interaction between block and treatment, so batch between treatment formulation and batch or block, that occurs. Okay. Similarly, an interaction can occur between treatment and block if the response is measured in the wrong scale. So here is an example. We may have a multiplicative or interaction relationship such that yij is equal to mu sub tau I times beta sub j. Okay. If we take the natural log of both sides of this, though, and in statistics we're always using the natural log, but we always write it as just the log, so a little confusing until you get used to it. So if we take the log of both sides of the equation, we get log of yij equals log of mu sub tau I plus log of beta j, and thus our model becomes additive by taking that log. Okay? But it's additive in the log scale, not in the original scale. Now, what we could do is we could use the log of each quantity to get a linear model, do the analysis, and then use the inverses to get back to our original units. Okay, so you could do that. You could take the log of all 3 quantities, and then then when we're done, we take e to the log, and remember that e to the log of a is equal to a. So we get back to the original value, a. Okay? Not all interactions can be eliminated, though, by using transformations. In fact, in our chemical example, we could not remove the interaction, so the interaction will render our results useless. I cannot emphasize that enough. It becomes useless, and we'll show why that is in a little bit, okay? If interaction exists, we need to use a factorial model, not a randomized complete block design. And this will be chapter 5, which we'll discuss after this chapter. Okay? And we're not going through this entire chapter, chapter 4. There are the Latin square design, and then there's I think it's a randomized complete block design, but it's like a partial one. So let's see, what do they say it's called? Balanced incomplete block designs. And those are pretty tedious. So we want to talk about as many different models as we can. So we're going to skip those and go on to some other models so you can see, be exposed to some other methods. Okay. All right, that's it for this video. I hope this has helped you understand about fixed effects and the randomized complete block designs. If you have questions, come to virtual office hours. I'm happy to help you. If you need an answer or want an answer prior to coming to office hours, then by all means, email me. I'm happy to help you. If it's about a problem, then please send me a picture of the problem so I know what you're talking about, because I may not have it available wherever I am. And also a picture of your work so that I can see how you're approaching this, and then I will get back to you as soon as it's possible for me to do so. Please take care of yourself. I hope you'll stay safe, because we'd love to see you here next time.